Hi guys, we were talking about function inverses, and I think we had the opportunity in both cohorts to go through these first couple of slides. Okay, so what happens here, okay, is if a function has an inverse, what happens is that the original function, the domain and range, gets switched. So the domain of the first function becomes the range of its inverse, and the range of the first function becomes the domain of its inverse. And so obviously you have to figure out what is this function, okay, to find the inverse, okay? And we said that we can test a function to begin with, okay, to see whether or not it has an inverse by applying the horizontal line test. Okay, so if you had something like this, okay, where all horizontal lines only intersect at once, then this function has an inverse everywhere. Okay, but if you look at a function like this, where it doesn't pass the horizontal line test, because obviously you can find a whole bunch of horizontal lines that intersect it more than once, okay, that this would not have an inverse everywhere. It might have an inverse on some intervals, but not the entire interval. Okay, and then we had the opportunity to take a look at this. I think it was in cohort B. Okay, cohort A, we kind of ran out of time when I saw it yesterday. So to find an inverse, these are the steps you use. Okay, so the first thing we want to do is, can we verify that the inverse exists by using the horizontal line test? So we would definitely check there. Okay, then you want to get it out of function notation. So if it's in f of x equals or g of x equals or any function notation, get it out of function notation just by replacing the f of x or g of x or h of x, whatever it is, with y. Okay, so then we want to change all the x's and y's. So all the x's become y's, all the y's become x's. Okay, once we do that, we solve for y. So we're going to isolate y. Okay, and then it's customary to go back to function, okay, notation. Okay, and in function notation, rather than saying f of x, we use this notation, which looks like f to the negative first power, but really what it means is f inverse. Okay, so this guy right here, okay, is f inverse. Like that. That's how you read that. Okay, I know it looks like it's f to the negative first, but that's not how you read it. Okay, and then lastly, if we can do that, you would want to demonstrate the domain of the original function is the range of its inverse, and the range of the original function is the domain of the inverse. And this stuff right here is where things get a little tricky sometimes. Okay, and so sometimes what we have to do, okay, is to have an inverse, we would have to restrict the domain of the original function, f. Okay, you got to restrict the domain of f for it to work out. Okay, so for instance, this guy coming back here, obviously just y equal x squared. It doesn't have an inverse everywhere, but if I restrict the original domain, okay, on some restricted domain, some interval that's a subset of the whole domain, it very well could have an inverse. It just wouldn't have an inverse everywhere, okay? All right, so we'll just keep referring back to this guy. All right, so I know one of the cohorts, and I think it was cohort B, we did these first couple of problems because we had a little bit more time, but I know with cohort, whatever cohort was here yesterday, okay, I can't remember which one, we didn't get to these, so I'm going to do them. So if you already saw this problem, okay, and this problem, you can skip ahead, okay, in the video, okay, until we get to this guy, which I know nobody saw. Okay, so let's start here. All right, so again, I'm going back to this and I'm just following this sort of guideline here, okay? So will this guy have a function? Well, if we take a look at this is just a line. That's all it is, okay? And so if you look at the graph, and it's just a sketch, it's not going to be perfect, okay? We're going to have a y-intercept at 7, okay? So it's going to go through 7 on the y-axis, and it has a negative slope, so I know it has to be a decreasing line. It has to go down from left to right. So it'll look something like this, okay? And then if I apply the horizontal line test, no matter what horizontal line I choose, it's only going to intersect it exactly one time. So this guy will have an inverse everywhere. Okay, so we go here and we say, okay, what's the first thing we do? Okay, well, we get rid of the function notation, replace it with y. So the very first thing we'll do is, take this g of x and throw it out and rewrite it as y equals negative 2/5 x plus 7. Okay, very first thing. Now the second thing we do, okay, again, okay, well actually it's the third thing. This was the first thing up here. Okay, this was the second thing. Okay, and this was the third thing. Okay, it doesn't make any difference. Okay, we know what we're doing. Okay, so we have to change all the x's to y's and all the y's to x's. Okay, so this guy becomes an x. And this x becomes a y. Okay, and so after I do that, I have to solve for y. Okay, so we solve for y. All right, so I take this guy and I got to get y by itself. So take the 7 and move it over so it becomes negative. So I get x minus 7 equals negative 2/5 y. Okay, now I want to get rid of the negative 2/5, so I could divide everything by negative 2/5. That's one way to look at it. Or I can multiply everything by the reciprocal of negative 2/5, which is negative 5/2. Okay, and so I would get a negative 5/2 x plus 35 halves equals, well, negative 2/5 times negative 5/2 is 1, so I just get y. Okay, so I solved for y, and then I go and I replace that with my function inverse, f inverse, okay, notation. In this case, we're working with g, so I'd replace it with g inverse. Okay, so g inverse of x is just this guy right here, negative 5/2 x plus 35 halves. Okay, and so there is my inverse of g right there. Okay, and obviously that's just another line. Okay, that's all it is. Okay, and so if you take a look at that guy, okay, and again, it's just a sketch. Okay, well, it would have obviously a y-intercept at 35 halves, which is 17.5. So it'd be way up here at 17.5. And it has a negative slope. It's just a little steeper than the original slope. Okay, and so that guy would be coming down like this, and you just have another line. Okay, so this graph would be the graph of the inverse of this function. Okay, and so the last thing we do is see whether or not we can demonstrate this. Okay, so let's see. Okay, that guy. All right, so the original function, okay, which is g of x, okay, not f of x, g of x. Okay, so can I take a look at what's the domain and what's the range? Okay, well, if we go back to the graph here and I take a look at, well, what x values are included in the domain, notice that every single x value along the x-axis, okay, will be included in the domain. So we could say, okay, the domain is the set of all real numbers, or if you wanted to write it as negative infinity to positive infinity, that works. And then we look at the range. Well, again, every single y value is included in the range because this guy just keeps going up and keeps going down. So again, you get the set of all real numbers, or if you want to put it in interval notation, you can do this, okay? All right, then if I look at g inverse of x, okay, and I look at the domain and range of that, so I go to this graph, Well, notice the same thing's happening. Every single x value is used up, okay? Because I can put any value at all in for x here, and it'll spit out a y value at me. So I get the set of all real numbers, okay? And now I always use the capital R for just a set of all real numbers. But again, if you want to go interval notation, you can do that. And then if I look at the range, once again, every single y value along the y-axis, okay, will be included. So we get the set of all reals, okay? And you can take a look at, are the domain and ranges switched? Well, the domain here is the same as the range there, and the range here is the same as the domain there. So this guy has an inverse everywhere. Okay, let's take a look at another one just like that. Okay, once again, okay, if I take a look at the graph of that guy, okay, and again, it's just a sketch. It's not going to be perfect, doesn't need to be perfect. Okay, it goes through -9 on the y-axis. So it's going to go through -9. It has a positive slope, which means that it's an increasing line. So it goes up from left to right. Okay, so sort of like that. And again, you take a look at horizontal lines. All horizontal lines will only intercept that graph once. So it passes the horizontal line test, which means that it has an inverse everywhere. Okay, so the first thing we do is get it out of function notation. So take the h of x and replace it with y. So y equals 1/4 x minus 9. Okay, then we switch the x's and y's. So the y becomes an x, and the x becomes a y. 1/4 y minus 9. And now we solve for y. So I got to get the 1/4 y by itself, so move the -9 over, becomes +9, so I get x plus 9 equals 1/4 y. And then the easiest way to get rid of 1/4 is just multiply everything by 4. Okay, so I would get 4x plus 36 equals 1y, or just y. Okay, and then we go back to function inverse notation. Okay, so let's see, this is h of x, so I'd say h inverse of x equals 4x plus 36, okay? And this will be my inverse function. And if we take a look at that guy, again, it's another line, that's all it is. Okay, notice that it goes through positive 36, okay, on the y-axis, and it has a slope of 4, so it's just steeper than this guy. So it'd be something like, oh, that's bad, something like this, okay? And notice again, okay, it's just a line, okay? That's all it is. And then the last thing we look at is, can we take a look at the domains and ranges of both of these? So if I look at h of x and look at its domain and its range, well, go here, and obviously every single x value is included there. Okay, so the domain would be the set of all reals. And then I look at the range, every single y value would be included in the relation. So the range is the set of all reals. And then if I look at the domain and range of the inverse function, okay, clearly it's going to happen again. Okay, so the domain here would be all reals, and the range would be all reals. Okay, so again, the domain of the original function becomes the range of the inverse function, and the range of the original function becomes the domain of the inverse function. So everything works out nice and clean. And that's going to happen with increasing and decreasing lines all the time. Okay, it works all the time. Okay, so this one I know nobody saw. And it looks a little different than the last two, but believe it or not, that is a line, okay? Because I could distribute the division here and here, and I could rewrite that as g of x equals 2/23 x minus 9/23. So again, that's just a line again, okay? So we take a look at what does that guy look like. Well, it goes through, okay, negative 9/23, okay, on the y-axis. So we'd have our negative 9/23, and then it has a positive slope, so it's going to be going up from left to right. It's just the slope is not very high, so it kind of goes up gradually, okay, like that. Okay, so notice that it passes the horizontal line test. Every horizontal line will only intersect it once. So it definitely has a function inverse everywhere, okay? So it passes the horizontal line test, okay? So we get it out of function notation, replace the g of x with y, so we get y equals. Okay, now you could work with it in this form here, or you could work with it in this form here. It doesn't make any difference. Okay, it's just a matter of what you want to work with. So I'm just going to go back to the original guy. Okay, and so I get y equals 2x minus 9 over 23. Okay, so we take the y's and make them x's, take the x and make it a y, so we get x equals 2y minus 9 over 23. And then I just solve for y, okay? All right, so when I solve for y, I have to get this 2y by itself. So the first thing I'm going to do is multiply both sides by 23 to get rid of that denominator. So I get 23x equals 2y minus 9, and then add 9 to both sides. So I get 23x plus 9. Can't forget that x equals 2y. And then just divide everything by 2, okay? So I'm going to get 23 halves x plus 9 halves equals y, okay? And then just replace the y, okay, with my function inverse notation. So this will be g inverse, okay? So g inverse of x will just give me 23 halves x plus 9 halves. Now, if you wanted to, you could combine these because they have the same denominator, and you could put it in a form that's very similar to the original one. You could leave it this way. There's nothing wrong with that. So you could write this as g inverse of x equals 23x plus 9 all over 2. So either one of those guys is 100% correct. Okay? And then we just take a look, you know, what's going on here? Well, if I take a look at the graph here, it'll help me out a little bit, okay, to illustrate, you know, how the domains and ranges work out with each other. Okay, so let's see, if I look at this guy, it goes through 9 halves, okay, so it goes through 9 halves on the y-axis, and it's got a pretty high slope. I mean, that slope would be 11.5, so it's pretty steep, okay, so it's going to be relatively steep like this. Okay, and so if I take the original function g of x and look at its domain and range and compare that with the domain and range of the inverse, g inverse of x, okay, things will work out again, okay? So with g, we go here, and you notice that every single x value is accounted for, so the domain is a set of all reals, and every single y value is accounted for, so the range is a set of all reals. And then if I go over here, the same exact thing happens. Okay, the domain is a set of all reals, and the range is a set of all reals. So notice again, the domain of g is the same as the range of g inverse, and the range of g is the same as the domain of g inverse. Okay, so that's why things work out nice and clean. Okay, that'll wrap it up for the first video.